Hello everyone, welcome to my talk. My name is Kedar Bidarkar. I am Senior Quality Engineer working at Red Hat from India. And today I'll be talking about KubeVirt. So who is familiar with KubeVirt? Anyone? Okay, nice. So who is familiar with Kubernetes? Oh, lot many folks. So let's get started. So this is the agenda of my talk today. So we'll look at why and what is KubeVirt. Then we'll look at the basic KubeVirt objects and components. After that, we'll look at the deployment and management of virtual machines. And then we'll touch base upon the basics of KubeVirt storage and networking. And finally, we'll have Q&A. So currently, we have on-premise solutions like OpenStack, Overt, and then we have the public cloud providers like AWS, GCP, Azure, etc. So when we already have these, why KubeVirt and why VM management stuff again? Many new workloads are continuously moving towards containers, but virtualization is here to stay for the foreseeable future because of various business reasons and technical reasons. And so what would happen is both these environments would coexist for some time to come. And so multiple workloads would need multiple stacks. So as you can see here, the VM workload would need VM stack, and the container workload would need container stack. But this would lead to duplication of efforts in trying to manage, operate, and thus increase the costs, as each stack would have its own set of cluster hosts, storage, and network setups. So rather than running multiple workloads on multiple stacks, why not run multiple workloads on a single stack? So using KubeVirt, what we could do is we could run multiple workloads on a single stack. So over here, we can see the VM workload is running side by side the container workload on one single Kubernetes cluster. So here, the virtual machines are running inside the Kubernetes pods. So with this unified infra, it should be easier to manage, operate, and thus reduce the costs. Also, this would help in providing a migration path wherein the migration of workloads from VM to containers will be on the same infra. So the virtual machines that are running on Kubernetes, they would be making use of this, the Kubernetes concepts like load balancing, rolling deployments, and so on. So this is what we were talking and discussing about. So you can see the business reasons could be the cost required to containerize, the time to market, and also some applications which are already towards end of life. Then the technical reasons would be certain applications which would require custom kernel, and there could, of course, be some applications which are very hard to containerize. So now let's look at what is KubeVirt. So KubeVirt is a Kubernetes add-on that enables scheduling of traditional VM workloads side by side the container workloads on Kubernetes. So it makes use of custom resource definitions and a bunch of controllers. So it extends the existing Kubernetes cluster by providing a set of Virt APIs. So it works by running libvirt kvm inside a container. So now let's take a look at KubeVirt installation. So to get started, or if you want to quickly try out KubeVirt, you can make use of Minikube, which is a single node Kubernetes cluster running inside the Minikube VM. So as we are using here a Minikube VM, so we need to enable nested virt on the bare metal setup. And for folks who do not want to do that, we could also use the emulation mode. Also, we require the kubectl binary to deploy and manage the virtual machines. So what we do is, for installation of KubeVirt, we make use of the kubectl binary and apply the release manifest of KubeVirt. So we apply the KubeVirt operator, which would create the KubeVirt namespace and KubeVirt custom resource definition, and a bunch of other stuff like cluster role, service accounts, and so on. After that, when we apply the KubeVirt CR, what happens is it would fetch the Virt component images from the container registry, and it would create the Virt component pods inside the KubeVirt namespace. So once these Virt component pods are up and running, we can say that the installation of KubeVirt is completed. So what are the benefits with KubeVirt? So it drops directly into the existing Kubernetes cluster. No additional host setup is required. As you can see, it was simple to install. Also, it provides a transition path wherein the VMs can make use of the Kubernetes infra, tools, and management stuff. Also, not all applications are easy to containerize. There could be certain applications which are difficult to containerize, and it is for these applications, what we could do is we could make use of KubeVirt and deploy them on Kubernetes as virtual machines. So it also lowers the entry load for the migration of applications to Kubernetes. So there is no need for us to containerize the applications before the migration to the Kubernetes. So KubeVirt provides not just the infra convergence, but it would also provide a workflow convergence. So next, we are looking at the KubeVirt architecture. So the grayed out components are the KubeVirt components, and the others are the Kubernetes components. So one thing to note here is that KubeVirt supports not just the Docker runtime, but it also supports the CRI-O with runc. So now we'll look more closely at the Virt components of KubeVirt. So Virt operator. So it handles the installation, removal, and upgradation of the KubeVirt application. Then we have the Virt API. So Virt API is very much similar to the Kube API server. So it deals with validation and defaults of virtual machines. And it also acts as an entry point for all Virt-related flows. Then we have the Virt controller, which is very much similar to the controller manager from the Kubernetes world. So this is where all the controllers and the logic lives. Then we have the Virt handler, so which is very much similar to the kubelet, which is a node daemon running on each of the nodes of the Kubernetes cluster. So Virt handler is all about managing the VMIs which are running inside the pods, which are managed by the kubelet. Finally, we have the Virt launcher pod, or the Virt launcher component, which provides C groups and namespaces to host the virtual machines. So for every VMI object, a corresponding Virt launcher pod gets created in the same namespace. So within this Virt launcher pod, we will have a compute container, which would have a local libvirt instance running inside it. So now we'll take a look at the KubeVirt objects. So there are various KubeVirt objects. We have the virtual machine instance, virtual machine, then we have the virtual machine replica sets, similar to the pod replica sets, and then we have the virtual machine presets. So we'll look at now the virtual machine instance object. So virtual machine instance is a running VM. So virtual machine instance, just like the pods, has its own kind. So it is scheduled as a pod, and it lives inside the pod. So on the right-hand side, we have an example of a VM spec file, wherein we are defining various parameters and specs, like the CPU, memory, and also the storage, which is here the containerDisk. And also the applications within VMI are exposed using the service. So here is an example wherein we are exposing the port 22, which is the SSH port, and we are making use of the cluster IP service. So using that, we can log in into the VMI. So how do I create a new VMI? So what we do is we make use of the kubectl binary and apply the VMI manifest. And once we do that, we'll have a Virt launcher pod. So if we are using containerDisk as the volume, we'll have two containers running inside the Virt launcher pod. So the first one would be the compute container, and the second one would be the volume container disk. So once these two containers are up and running, we would have our VMI up and running. So once the VMI is up and running, we can connect to it using the virtctl binary and use the console command. So using that, we can log in into the operating system. So you might be wondering, so if it is making use of libvirt kvm, so where is my domxml file? So where do I find the domxml file? So you would find the domxml file of your virtual machine inside the compute container of the virt launcher pod. So as you can see, once we log in into the compute container of the virt launcher pod, we can use the virsh commands to list the virtual machine that is running, and we could then navigate through the file system to locate the domxml file, or you can just use the virsh dumpxml to go through your domxml file. So that was about the VMI object. So now let's look at the virtual machine object. So virtual machine provides additional management capabilities to VMI inside the cluster. So it provides AVI stability. It also provides a way to do offline configuration changes and also manage the lifecycle of the virtual machines. So on the right-hand side, we have an example of VM spec file. So the section specific to the VM would be the template section. So you may be wondering, like, what is the difference between a VMI and a VM object? So the VMI would have just two events, just create and delete. But the VM would have create, start, stop, restart, and delete. So how do I create a new virtual machine? So creating a new virtual machine would be very much similar to creating a VMI. So we make use of the kubectl binary and apply the VM manifest. So once we do that, a VM would be created. But as you can know, the VM is currently not in a running state. So we need to make use of the virtctl binary and start the virtual machine. So once the VM is in running state, we can notice that the VM is now, OK, so once we use the virtctl command and start the virtual machine, now you can notice that the VM is in a running state. So post that point, it will be very much similar to a VMI. So you would have a virtual, you'll have a virt launcher pod, and then once the pod is up and running, you would have the VMI. So let's now discuss about the virtctl command. Yeah. Yeah. So we can still make use of the kubectl binary for basic VMI operations, but we would require the virtctl binary for advanced features like accessing the serial and graphical console, and then also to manage the lifecycle of the virtual machines. So just like kubectl binary, virtctl binary is deployed and is used from the client side. So these are the various virtctl commands. You can start, stop, restart, and then if you want to access the serial or graphical console, you can make use of console and VNC. So now let's talk and discuss about KubeVirt Storage. So up until now, we were looking at various VM and VMI spec files, which were making use of containerDisk. So now let's take a look at what exactly is a containerDisk. So with containerDisk, what we do is the VM disks are placed on container images, and these container images are pushed to the container registry. Then what we do is these disks are then pulled from the container registry, and then they reside on the local node hosting the VMs. So one thing to note here is that container disks are ephemeral storage, and they are not suitable for persistent storage. So below is an example wherein we are creating our own container disk. So what we do is we make use of the KubeVirt container base image, and we add the Fedora QCow2 image under the /disk directory structure. So one thing to note here is that the currently supported formats for the VM disks are QCow2 and raw disk image format. So if you have your VM disk in any other format, you need to first convert it into QCow2 or raw disk image format. So now let's look at the containerized data importer. So containerized data importer is not part of the KubeVirt, but it is a part of a sister project called the CDI, which is Containerized Data Importer. So it provides persistent storage management add-on for Kubernetes. So its primary goal is to build VM disks on PVCs for the KubeVirt VMs. So this is all to deal with persistent storage for the virtual machines. So we have three use cases over here for the CDI. So we can import the disk images from URL to PVC by making use of HTTP or S3 as the source. Then we could upload the local disk image onto the PVC, and you could finally also clone an entire existing PVC. So CDI, just like KubeVirt, we need to install it. So we need to first apply the CDI operator manifest and then the CDI operator CR manifest. So once we do that, we'll have some CDI pods which get created under the CDI namespace. So up until now, we were looking at the VM spec files, which were making use of the container disk, which was ephemeral storage. But if we need to provide persistent storage, we need to make use of persistent volume claim. So as you know, with Kubernetes, the way we go about providing persistent storage is make use of persistent volume claim. So with persistent storage, what we do is the VM disks are placed on the PVC. So the persistent volume claim requests storage from the PV, that is the persistent volume, which can be either in file system mode or in a block mode. So below is an example wherein we are doing two things. We are first creating a PVC, and then we are importing the Fedora QCow2 image onto the PVC by making use of the CDI annotation. So once the PVC creation and the import of Fedora QCow2 image is completed, then we could start the VM which makes use of the PVC. So now let's look at the data volume. So data volume is an improvement over the persistent volume claim. So data volume is a custom resource which is provided by the CDI project. So it provides integration between the KubeVirt and CDI project. And it also automates both the PVC creation and importing of the VM disks onto PVC during the VM launch flow itself. So the VM is not scheduled until the data volume is created and it is in a success state. So here the KubeVirt is aware that it is not supposed to start the VM unless the data volume is in a success state. So this is an example wherein we are using the data volume instead of the persistent volume claim. So in this example, we are making use of just one spec file, and we are doing three things. We are creating first a PVC, then importing the Fedora QCow2 image onto the PVC, and then once the PVC creation and importing is completed and is in a success state, that's when the VM would automatically launch. So the advantage of data volume over PVC would be that we don't have to wait for the PVC creation and importing of the disk to complete before starting the VM. So now let's take a look at KubeVirt networking. So connecting a VM to network consists of two parts. So the first one would be the interfaces, which is the front end, and next one would be the network, which is the backend part. So for every interface, there should be a corresponding network with the same name. So on the right-hand side, we have an example wherein we explicitly specify the interfaces and networks. So in the earlier examples of the VM spec files or the VMI spec files, we have not been explicitly mentioning or making use of interfaces and networks. So if interfaces and networks are omitted, then the default values for those would be bridge and pod. So as I was mentioning, that if interfaces and networks is omitted, then the virtual machines are connected to the regular pod network. So what happens here is the virtual machine would own the pod's MAC address and IP address, and the pod's MAC address is randomized, and the IP address is deleted. So from the outside, there would be no difference between a VM and a pod. So KubeVirt does not bring in any additional networking plugins, but it makes use of various existing plugins like OVS CNI plugin and the Multus CNI plugin. And of course, there could be other plugins as well. So this is about the network interfaces. So it describes the properties of virtual interfaces as seen inside the VM interface. So it can specify various properties like models and so on. So each interface should declare its type. So if we omit the interfaces, then by default it would be the bridge interface. And then of course we have the various other interfaces types like masquerade, SRIOV, and so on. So this one is about the network types, which is the backend part. So each network should declare its type. We have the pod, Multus, and Genie. So the pod is the default Kubernetes network, and Multus and Genie are the secondary networks which are used for providing multi-networking support for the VMs. So below is a so in the below example, what we are doing is we are defining a network which makes use of the OVS CNI plugin. So a VMI which is making use of this network would be connecting to the Open vSwitch bridge BR1 and VLAN 100. So on the right-hand side, we have an example wherein the VM is connecting to 2 interfaces and 2 networks, and thus it is making use of multi-networking stuff. So these are the various other KubeVirt features. So we also have support for the live migration, wherein you can live migrate a virtual machine from one node to another node with 0 downtime. So this could be useful when you want to place one of the nodes under maintenance of Kubernetes. Then we have a web UI for KubeVirt, wherein you can manage and deal with the various KubeVirt objects and various entities. And then finally, we have the Foreman KubeVirt plugin. So this plugin is not part of the KubeVirt project, but it is part of the Foreman project. I thought I'll just mention it over here. So what you could do is you could add KubeVirt as a compute resource in Foreman, and you could also launch virtual machines on KubeVirt from the Foreman side. So I think, so for folks who are interested in collaboration, we have the website, KubeVirt.io. We have a wonderful user guide. And then we have the GitHub, wherein we can raise issues. You can ask for feature requests. And then we have the mailing list, Slack, and IRC. And then Q&A.
Sorry, my microphone wasn't ready yet. Thank you again, Kedar. Thank you. Sorry for the sound problems or problems with the headset. I will have a closer look at it afterwards.
Dropping down.
Yeah, okay. See. Are there any questions in the audience? Okay. I don't think there are any. I guess you will attend the evening event as well?
Yes.
Okay, so get in touch with him again and ask him your questions you didn't want to ask in the audience. Thank you.
Yeah, thanks.